Welcome to the deep dive. We're pulling back the curtain today on something kind of invisible that powers our digital lives. Think about it. Every search, every stream, every scroll, it all runs through these massive data centers. But have you ever thought about the environmental cost? Specifically, water. It turns out our cloud is, well, it's really thirsty.
It really is an invisible thirst, you could say. And honestly, it's becoming one of the most critical sustainability challenges we're facing right now.
Invisible thirst. I like that.
Yeah, the sheer amount of water needed just to keep these places cool is staggering. It's finally starting to get the attention that it deserves, though.
Right. So if it's such a big deal, this invisible thirst, what are companies actually doing about it? How are they tackling it?
Well, that's what we're digging into today, isn't it?
Exactly.
Huh.
That's our mission. We're going deep into the water demand for cooling, looking at the sometimes pretty ingenious solutions tech giants and cities are cooking up. And we'll highlight these public-private partnerships, which seem crucial for making it all work sustainably. So this is basically your shortcut to getting smart on a really important kind of behind-the-scenes sustainability push. Expect some eye-opening facts, real examples, and maybe a few aha moments about these systems we rely on but rarely see.
Yeah, it's funny. We're all so aware of, using our devices, but the actual physical stuff behind it, the infrastructure,
Yeah.
and its resource demands, it's mostly out of sight, out of mind for most people.
Okay, let's start unpacking that. Data centers. They're not just big sheds with servers, right? They have some fundamental needs to even function. What are we talking about foundationally?
Right. At the absolute core, you need, first, super reliable power, like incredibly reliable, often multiple sources so there's zero downtime.
Okay, power. Makes sense.
Then you need massive network connectivity. Think high bandwidth fiber everywhere to handle all that data flowing in and out constantly.
Got it. Power, connectivity.
And of course, security. Both physical security guards, fences, the works, and cybersecurity. Protecting the data is paramount.
Absolutely. Foundational stuff. But our sources keep pointing to one thing as the most resource intensive, even more than power in some ways, in terms of direct environmental impact. That's cooling. Why is cooling suddenly such a huge deal? Especially now.
This is where it gets really interesting. And, kind of concerning. Think about it. Every single calculation a server makes generates heat.
Right. Basic physics.
But now, computing demand is exploding,
Yeah.
especially with AI, machine learning. These tasks are incredibly power hungry, which means they generate way more heat than traditional computing.
So it's not just more computing, it's more intense computing.
Exactly.
Yeah.
More intense computing, disproportionately more heat,
Yeah.
and all that extra heat. It needs much, much more cooling. It's this relentless cycle.
Okay, that makes sense. That's why cooling is the big focus for sustainability now.
Precisely.
And the numbers, they really are something. We're not talking about a garden hose here.
No, not at all. Get this. Here's a stat for you. A single data center, just 1 megawatt of capacity, which isn't even that huge these days, can use around 25.5 million liters of water a year.
25 million liters.
Per year, just for cooling.
Wow. How much is that in, human terms?
Well, to put it in perspective, that's roughly the same amount of water about 300,000 people might use in a day, depending on where you are.
300,000 people's daily water for 1 megawatt.
Yeah, that really changes how you think about scrolling through cat videos, doesn't it?
It certainly puts your digital footprint into a different light.
So is there a common misconception people have about this? Everyone knows about the energy use, right?
Yeah, that's the main one. People think energy, energy, energy. And data centers are energy hogs, no doubt. But the water story is much less known and much less visible.
And this massive demand, how does it actually play out on the ground, especially in places that are already, short on water? That's the critical intersection. Geography matters hugely. Our sources point out that loads of popular data center hubs, think Northern Virginia, Texas, California. They often have good power grids, yes, but they're also frequently areas with high water stress.
Right, places prone to drought.
Exactly. So it's not just about how much water they want to use, it's about what's actually available locally. The climate, existing water supplies, water rights regulations, which can be incredibly complex, and drought risk. All of this heavily influences what cooling methods are even feasible.
So access to things like reclaimed water would be a big advantage then.
A huge plus, yes.
Yeah.
But even then, you've got issues like how far away is the source, other legal hurdles, what does the extra treatment cost, is it available year-round? It's complicated.
Okay, so the traditional cooling methods are the really thirsty ones, using drinking water. What are the alternatives? How are companies moving, as you say, beyond the faucet?
Well, the traditional way, as you said, often uses these evaporative cooling loops. Water evaporates, takes heat with it, simple physics, but it needs a constant top-up, usually with potable water or drinking water.
Right.
A step up from that are hybrid or adiabatic systems. These mostly use outside air, which is great. They only use a bit of water evaporation for a boost on really hot days.
So they use less water, but
Yep.
still some water.
Correct. They significantly cut down water use compared to the old evaporative ways, but yeah, they often still need some makeup water.
But the really exciting stuff, the aha moments, seem to be around water reuse, getting creative. Can you give us an example? Who's doing cool things here?
Absolutely. Amazon Web Services, AWS, they've really been pioneers here. They're using reclaimed wastewater, which is essentially highly treated sewage, instead of drinking water for cooling in quite a few U.S. facilities, places like Virginia and California.
Wow, okay. So turning wastewater back into a resource.
Exactly. It's a really smart circular approach. And they've got this big goal to use recycled water for cooling 120 of their U.S. data centers by 2030.
120 data centers.
Yeah, and they reckon that'll save hundreds of millions of gallons of drinking water every year.
Mm.
It's not just fixing a technical problem, it's rethinking what we even consider waste.
That's genuinely impressive. Treating waste as a resource. And AWS isn't the only one, right? I think Equinix is also doing similar things.
They are, absolutely. In 2023, Equinix reported that about 25% of their total water use came from non-potable sources, mostly reclaimed water.
Okay.
And that's across major hubs like Singapore, Ashburn in Virginia, Silicon Valley. So you see this trend picking up, this move to diversify water sources.
And Google, I read about their setup in Douglas County, Georgia. That sounded pretty clever, too.
Yeah, Google's approach there is interesting. They use recycled treated effluent from the local wastewater authority. Now, effluent is basically wastewater that's already been treated, but it's not quite drinking water standard yet.
Okay.
So Google takes that effluent, treats it further on their own site, and then pipes it directly for cooling.
So an extra layer of treatment.
Right. And they've built in backups, too, on-site water storage, and they can switch to potable water if they absolutely have to. It shows this multi-layered thinking for reliability and sustainability. Proactive stuff.
Okay, this is all great progress using reclaimed water. But then I heard about Microsoft doing something even more radical. This zero water evaporation design. What's that about? Why is it such a potential game changer?
Yes. This is potentially a massive leap. Microsoft announced this in 2024, designing data centers that consume zero water for cooling through evaporation.
Zero water through evaporation? How does that even work?
Okay, so they're using two main things. One is chip-level liquid cooling. Think tiny little cooling systems directly on the computer chips themselves. Super efficient at grabbing the heat right at the source.
Okay, cooling the chips directly.
And the second part is using closed-loop systems. The liquid that picks up the heat circulates, gets cooled down elsewhere, and comes back around. It never gets intentionally evaporated into the air like in traditional cooling towers.
So it just cycles internally, no loss to the air.
Exactly. It completely eliminates those huge evaporative water losses we talked about.
Wow.
If this becomes widespread, it could fundamentally change the water footprint of data centers, especially in dry, water-stressed areas. It basically removes that whole water for evaporation problem.
That really does sound like a game changer. Maybe the new gold standard everyone aims for.
It could well be. Arguably, yes.
Okay, so amazing tech breakthroughs like zero evaporation cooling. But, even the best tech doesn't operate in isolation, does it? To really make these things work at scale, especially with something as vital as water, you often need, well, collaboration.
Absolutely vital. You really do.
And that brings us neatly to public-private partnerships.
PPPs.
Yes, PPPs are a really crucial model here, especially with data centers growing so fast. They basically combine the strengths of the public sector, like cities and water authorities, with the resources and innovation of the private sector, the tech companies.
So why do they matter so much? What's the real advantage of setting them up this way? Well, looking broadly, there are several big benefits. First, they bring in private money, private capital. That takes a huge financial load off public budgets, which are often stretched thin.
Right, saves the taxpayer upfront costs.
Exactly. They also allow shifting some of the project risks, like construction cost overruns or operational issues, to the private partner, who might be better equipped to manage them.
Okay.
And you get to tap into private sector expertise in designing, building, and running these complex water treatment facilities. Plus, some models, like where one entity designs, builds, and operates the plant, can really speed up the whole project timeline, get solutions working faster.
And we have a prime example of this working in the real world. The Quincy water reuse utility. The QWRU in Quincy, Washington, a Microsoft and City of Quincy collaboration. Tell us about that one. How did it work?
Right, the Quincy QWRU is a fantastic case study. It's basically a purpose-built circular water reuse system. And its real cleverness is how it blends different water sources.
Okay, so not just one source.
No, it's diversified. In summer, when cooling needs are highest, it takes water from a nearby irrigation canal, part of the Columbia Basin project.
Okay, canal water.
It also uses a tiny bit, maybe 5%, of potable groundwater, just for backup reliability. But the key part is it takes municipal wastewater, effluent treated sewage again, and also industrial blowdown water, and treats that for reuse and cooling.
Hang on, blowdown brine. What's that exactly?
Ah, yeah. Blowdown is basically the wastewater left over from cooling towers or other industrial processes after a lot of the pure water has evaporated. It becomes super concentrated with salts and minerals.
So, really hard to deal with usually.
Notoriously difficult and costly to dispose of because it's so concentrated. But the QWRU system is designed to treat and manage even that.
That sounds incredibly sophisticated, juggling all those different water types and treatments. How did they structure the partnership itself? Who owns it? Who runs it? How do they make it fair?
The structure is pretty clear, which is probably why it works. Microsoft put up the money, the capital investment to build the whole thing.
Okay, Microsoft paid for construction.
But the city of Quincy actually owns the facility and operates it day to day.
Interesting.
And the contract between them is built to be flexible. Things like water rates can adjust based on usage. And really importantly, it allows other data centers in the Quincy area to potentially connect to the system too, under cost-sharing agreements.
Oh, so it's not just for Microsoft. It could become a regional solution.
That's the idea.
Yeah.
Fostering a broader benefit, not just one company.
This really sounds like a win-win. What were the main positive outcomes for Quincy and for Microsoft?
The upsides were significant, yeah.
Mm.
For the city of Quincy, the big one is less demand on their precious drinking water supply. That's huge for resilience.
Especially in a potentially dry area.
Absolutely. It also meant lower overall costs for treating the city's wastewater because some of it was being productively reused. And it definitely boosts their drought resilience because they're not just relying on one source anymore.
Right.
Plus, it provides a better way to manage those tricky waste streams, like the blowdown brine, and they designed it with room to grow so it can scale up as more digital infrastructure potentially arrives. A really solid model for how a city can partner up to secure its water future.
It sounds great. But I imagine a project this big, this complex, it couldn't have been all smooth sailing, could it? Even with a strong partnership, there must have been hurdles.
Oh, absolutely.
Yeah.
You're right.
Yeah.
No project this ambitious is easy. One huge factor was just the time it took.
How long?
About 10 years. From initial planning to full operation.
10 years? Wow.
Yeah, this wasn't just plugging something in. They had to design and build completely new, advanced water treatment facilities from scratch. That takes immense engineering effort, permits, everything, and serious financial commitment.
Okay, 10 years is a long haul. What else?
Well, that irrigation canal they use, it's seasonal. It actually runs dry in the winter.
Oh, right. So they have to switch sources completely.
Exactly. They have to rely on the other sources, like the treated effluent and groundwater, during those months. Requires careful management. And another thing is geography, the physical layout, means not every data center facility in the area can easily or affordably connect to the QWRU pipes. So it's a great solution, but not necessarily one that reaches everyone everywhere, even locally.
That coordination over a decade sounds tough. And even if you get the city, the company aligned, there's the public, right? People might worry about their water being used this way or potential pollution. How do you handle that?
That's a massive challenge, and it's very real. Public perception is critical. People understandably get anxious. You hear concerns about, is this taking our drinking water? Or what happens if there's a leak of this treated effluent? Or even just noise from the new plant?
Yeah, and I'm in bialism, but with water.
Sort of. And if you don't engage with those concerns openly and early, public opposition can seriously delay projects or even stop them entirely. Building trust is just absolutely essential right from the start.
And once these fancy reuse systems are built, running them isn't cheap either, is it? It's not just the upfront cost.
That's a very important point. These advanced treatment methods, things like reverse osmosis or ultrafiltration, needed to get the water quality right. They have higher capital costs, sure, but also significant ongoing operational costs.
Like what?
Well, regular maintenance, for one. The energy needed to run the pumps and purification processes can be substantial. Then there are the chemicals used in treatment. And remember that concentrated blowdown brine we talked about? Disposing of that safely and legally is complex and expensive in itself.
So you have to budget for all that long term.
You absolutely have to factor those O&M operations and maintenance costs into the whole equation for the long run, or the system might not be financially sustainable.
Okay, cost is one thing. What about the water quality itself? Using treated effluent. It sounds okay, but is it good enough for these really sensitive, expensive cooling systems?
Quality assurance is paramount. It's a constant focus. Using reclaimed water, even highly treated effluent, does carry risks. You might have slightly different mineral content than potable water, maybe trace contaminants or issues with biofilm growth.
Things that could gum up the works.
Exactly. They could cause corrosion in pipes, scale buildup on heat exchangers, or just make the cooling less efficient. So the cooling systems themselves often need to be specifically designed to handle this type of water, or the water needs really precise, consistent treatment before it even gets to the cooling towers. It's a technical balancing act.
And looking forward, how on earth do they predict how much water they'll actually need? With tech changing so fast, AI booming, forecasting sounds like a nightmare.
It is genuinely difficult. Predicting long-term water demand is incredibly complex. For one thing, cooling needs swing wildly with the seasons, right? Much higher demand in the summer, especially with evaporative cooling.
Right, more evaporation when it's hot.
And then you layer on the projected growth, more servers, denser racks, and especially the explosion in AI workloads, which are just incredibly intensive. Trying to accurately guess the water needed 5–10 years down the line, it's tough. But you have to try, otherwise you might build infrastructure that's too small or way too big and expensive.
So we've laid out the challenges: time, cost, public perception, quality, forecasting. Given all that, what are the key lessons learned? What principles should guide these projects for long-term success and sustainability?
Okay, pulling it together. First, forecasting might be hard, but planning for flexibility is crucial. Build systems that can scale up or down, design them so you can switch between water sources depending on the season or availability, and be ready to adapt to changing regulations. Rigidity is risky.
Makes sense. Be adaptable.
Second, quality standards. Can't stress this enough. Reclaimed water needs rigorous treatment to meet appropriate standards. It is not raw sewage being pumped in. Filtration, disinfection, maybe advanced stuff like reverse osmosis. It's all essential to protect the equipment and, frankly, public health.
Right. It has to be fit for purpose.
Precisely. Third, transparency in the agreements. Those PPP contracts need to be crystal clear. Who does what? Who's responsible for treatment, for maintenance, for handling failures, for emergency backups? What are the financial terms? Clear contracts build trust and prevent disputes later. Quincy's a good model there.
Okay. Clear contracts.
Fourth, stakeholder engagement, and not just at the end. From day one, talk to local community, the water utility, the regulators. Build trust. Address their concerns honestly about water availability, environmental impact, the trade-offs. Get buy-in early.
Don't just spring it on people.
Never works.
Yeah.
Fifth, diversify your water sources. Don't rely on just one tap. Mix it up: potable, reclaimed, maybe canal water if available, groundwater.
Yeah.
That portfolio approach builds resilience against drought or other disruptions.
Like Quincy did.
Exactly. Sixth, always push to minimize evaporative loss. That's where the biggest water savings are, ultimately. Technologies like advanced liquid cooling, chip-level cooling, and especially Microsoft's zero-evaporation designs, they are the future for water conservation in this sector.
Aim for zero evaporation where possible.
That should be the goal. And finally, seventh, measure everything. Monitor and track water usage constantly, daily, seasonally. Know exactly where the water is coming from, how much reclaimed versus potable. Project future needs as best you can, and report on it transparently. You can't manage what you don't measure.
Measure, measure, measure. Got it.
That data is crucial for accountability, for adapting your management, and for proving that these systems are actually working sustainably.
Wow, what a journey. Okay, so we started with this idea of the massive hidden water thirst of our digital world. We looked at the ingenious solutions tech like AWS using reclaimed water, Google's multi-layered system, and Microsoft's potentially game-changing zero-evaporation cooling. And we saw how critical those public-private partnerships are, with Quincy as a prime example. It's incredibly complex, isn't it?
It really is multifaceted. And it's clear that as our digital lives keep expanding, especially with AI just exploding, the pressure on resources like water is only going to get more intense. So these innovations, these collaborations we've discussed, they're not just nice to have, they're absolutely essential for a sustainable future. They directly affect the unseen machinery powering our everyday
It
lives.
really brings it home. This isn't just a tech issue, it's a community issue, a resource issue.
So precisely, and these partnerships show a path forward.
Okay, so today we peeled back the curtain on water in data centers. It leaves me wondering, as you go about your digital day, what other hidden resource challenges might be humming away behind the scenes? What other complex problems are maybe being quietly solved right now, or perhaps are still waiting for our collective ingenuity within this vast infrastructure we so often take for granted? Something to think about. Thanks for joining us on the deep dive.